Welcome everyone to Simplifying Radicals. This is a useful section for geometry and algebra, Algebra 2. It's used in a lot of cases, but this is kind of like a supplementary section. Let's go ahead and break it down. Now, first let's talk about the radical expression. The radical expression is composed of two parts. We have here what's called the radicand. That's underneath the sign, the house as I often call it, and this is the radical. Okay, so the radical is the sign, and the radicand is the number underneath the sign. Okay, so what are the conditions for simplifying? So what does it mean to simplify? It means the radicand has no perfect squares, perfect square factors. Okay, so there's no perfect squares underneath the radical. The radicand does not contain a fraction, and a denominator does not contain a radical. So those are the three conditions for simplifying. We got to make sure we abide by those three things. It's best when used in practice of these problems, so let's go ahead and break down some of these problems. Example number 1. We can clearly see that 16 is 4. Okay, the square root of 16 is 4. But why? Why is the square root of 16 4? Well, the square root of 16 essentially is saying what times itself twice equals 16. Okay, and the number is 4. 4 times 4 equals 16. So 4 times 4 equals 16. Another way to express this is 4 squared and the square root of that. 16 is the same thing as 4 squared. So if we take the square root of something that's squared, it's just going to undo the square root. Just as multiplication is the opposite of division, taking the square root is the opposite of squaring something. Okay, so if we have something and we square it, it's the same thing. It's the opposite of taking the square root. Okay, so they're opposites. So we know the square root of 81. We know this is 9. Okay, 9 times 9 equals 81. Now, if we were to break this down another way, okay, and I'm going to show you how. I'm going to do it with 16 and 81. I'll show you another way to do it. Okay, let me move this out of the way. So we'll go with 81 to start. So if we're looking at 81, another way to do this problem is by using a factor tree. Okay, and I always start by doing a factor tree and breaking it down into its prime numbers. So we're like, okay, 81, what's a prime number that we can divide by 81? I know most people would probably say 9 and 9, but in my experience, the best way is to look for prime numbers that are divisible by each number that we're doing. So for example, we know that 3 goes in 81, that's a prime number, and the other number is 27. 3 times 27 equals 81. And what we're going to do is we're simply just going to break it down into its lowest component. So we're going to get it into prime numbers. Now, anytime we have a prime number, we're going to try to find groups of those prime numbers. So we see a 3 and a group of 3s, okay? And we can rewrite this problem as the following. We can say the square root of 81 is the same thing as the square root of 3 times 3 times the square root of 3 times 3. You're probably like, what are you doing? This is just a roundabout way of doing this. Well, we can say that the square root of 9, same thing as times the square root of 9. Well, what's the square root of 9? The square root of 9 is 3, okay? Because we know that 3 times 3 equals 9. What's the square root of 9? 3. So what's that equal? 3 times 3? 9, okay? Now, what happens? When we do a factor tree, you're looking for pairs of numbers because anytime you have a pair, one of those numbers is going to come out of the radical. And whatever's left inside is going to be left inside. Now, whatever comes out of the radical gets multiplied together. So 3 times 3 equals 9. We already have established that. So the answer is 9. The same thing can be done with 16. If we break this down, it's 2, 8, 2, 4, 2, 2. We see that we have a pair of 2s. So 1, 2 is going to come out of the radical. So that's equal to 2. And then we have another pair of 2s times 2. 2 times 2 equals 4. So that's another way to do that. So if we look at example 3, we know this isn't a perfect square. A perfect square would be 25. So let's go ahead and try to break this down into its prime factors. So we have 2 and 10. We can break this down again, 2 and 5. Okay. Now, if you do square root of 20 on your calculator, just as an example, this is approximately equal to 4.47. So it's not a perfect square. So what is it equal to? How do we simplify it without using a calculator? Well, again, we're looking for pairs of prime numbers. Here's a pair of 2's. Okay, so that means a pair of 2's is going to leave the radical. So if we have our radical here, okay, a pair of 2's comes out of the radical. How does that work? Why does that work? Okay, and then and then the 5's by itself, it stays inside the radical. Now, why does it work this way? Well, we could rewrite this as 2 times 2 times the square root of 5. Well, we know the square root of 2 times 2 is the square root of 4 times the square root of 5. That's equal to 2 times square root of 5, 2 radical 5. Okay, anytime you have a pair of numbers, one of those comes out of the radical because that's the definition of a radical. A square root is what times itself twice. Well, what times itself twice equals 4? 2, clearly. Okay, but only one 2. We're not going to pull out 2 times 2. We just pull out 1. And that's why there's only 1 2 out in front, and it's 2 radical 5. Okay, let's do some more examples. Hopefully this will make more sense as we do more. Now, this time we have square root of 5 times square root of 10. There's a couple different ways to do this. One way to do it is to make this into square root of 50, and then break this down into its prime factors. Okay, so then we'd have 2, 25, 5, 5. What does that mean? Well, we would have, I'm going to leave this on this light green. We'd have 1 5 comes out, okay, and then I'm going to go pink. And then this 2, I like to box the ones that are going to stay inside the radical. This 2 stays inside the radical. 1 5 is going to come out of the radical, and we're left with 5 radical 2. Another way to show this is square root of 5 times 5 times the square root of 2. Those are all the prime factors. 5 times 5 times 2 is 50. So square root of 5 times 5 is 25. I know the square root of 25 is 5, so it's 5 radical 2. That's another way to show it. Another way to do this problem is to show that, let me rewrite it over here, square root of 5 times square root of 10. I know the square root of 5, square root of 10 is the same thing as the square root of 5 times 2. So I could rewrite this as square root of 5 times square root of 5 times square root of 2. Square root of 5 times square root of 5, anytime we have 2 square roots multiplied together like this, it's simply just going to give you what's underneath the radical, 5 radical 2. That's another way. So that's 3 ways that we can do that problem. Let's look at this one. I think probably the easiest way to comprehend is probably by multiplying the numbers first and then breaking it down into its factor tree. So we have 2 and 24. We have 2 and 12. 2, 6, and then 2 and 3. We're looking for pairs of number. Now you won't have a highlighter with you, but you will have a pencil. So let's go ahead and just circle the pairs of numbers that we have, and then we're going to box the ones that don't have a pair. You have to have a pair to leave the radical. You have to have a date to leave the house. That's what I like to say. So if you have 2 2's, one can leave the house. So square root of 48 is the same thing as, you don't have to write this every time once you got it. Okay, notice how I paired the numbers together. Why? Because then I know that's a perfect square. Okay, a perfect square is a number times itself twice. So that's 2 times 2 times square root of 3 equals 4 radical 3. And as you can see, we had 1 2 come out here, 1 2 come out here, and then 1 3 did not have a partner, so he stayed inside the radical. 2 times 2 is 4 radical 3, and that's how you do that one. Let me move this over so we can do 72. 72 is a little bit bigger, but we can still do it. I always, again, if it's even, start with dividing by 2. We get 36. Now here, if you recognize you have a perfect square immediately, like 36, we could continue factoring it and we would not be wrong there. But we can just say, okay, I know 36 is a perfect square. So I can rewrite square root of 72 as the square root of 2 times the square root of 36. Sorry, let me write it the other way around. The square root of 36 times the square root of 2. Well, I know the square root of 36 is 6 times radical 2, and now I know that I have it simplified. Okay, so that's even another way to do it. Look for perfect square factors, and then go from there. Okay, so we have a couple more conditions. I think we can get through all of these. It's fairly similar to what we did in condition 1. Actually, no, we're going to take a short break. I think I want to make sure we split this into suitable chunks. So that was condition 1. We'll pick up with condition 2 and condition 3 in part 2 of this video. Hope you've been enjoying so far. This is Simplifying Radicals.